When a metal is heated, it starts glowing red. As the temperature increases, it glows yellow, then white, and eventually even blue. Seems simple, right? But here's the twist. This simple looking phenomena actually broke the brains of the physicists in the 1800s and the 1900s. The confusion was, let's take a red flower for example. You might have heard, it reflects red and absorbs all other colors, that's why it seems red to us, right? That's when Gustav Kirchhoff stepped in and he asked, if the flower is constantly absorbing all the light except red, wouldn't it be accumulating energy? And because of this energy accumulation, wouldn't it just burn up? His answer, the flower doesn't store that energy, rather it radiates it out. He proposed a groundbreaking idea. Anything that absorbs energy also radiates energy. This re-emission of absorbed energy is now what we call as thermal radiation. At lower temperature, when the object has less energy, its thermal radiation is weak, mostly in the infrared range. But as the temperature increases, the energy of the object increases. The glow shifts from infrared to red, then to yellow, then to white, and eventually even blue, and even ultraviolet, which is not in the visible range again, but has a very high energy level. So what Kirchhoff did, he imagined a perfect object, which absorbs all the light energy but doesn't reflect any of it, and he called it a black body. When a black body's energy level increases, it radiates energy to maintain thermal equilibrium. The color of its glow depends upon its temperature, so a specific color corresponds to a specific temperature. This relationship is why we use Kelvin to describe the color of the light. Today, most lights aren't heated metals, they're LEDs. LEDs don't produce light through heat, yet we still use Kelvin to describe their color temperature because it helps us understand how warm or cool the white light appears in comparison to traditional heat-based sources. This standardization allows for consistent comparison across different lighting technologies. Now here's something funny. We just learned that hotter objects glow blue and cooler ones glow red. But on taps, blue means cold and red means hot. Why is that? It's simple. It's not science, it's just intuitive color association. We see red hues in fire, lava, and heated metals, so red feels hot. And we see blue in water, ice, and snow, so blue feels cold. That's why taps, ACs, and even graphics use this color scheme. It's easy to understand even if it is not scientifically accurate. So there you go. Heat causes objects to glow. The color of that glow changes with temperature. This relationship is why we measure the color in Kelvin. LEDs use Kelvin so that we can easily compare their lights with traditional sources, and taps use red and blue, well, because humans like shortcuts. If you found this video informative, like and share with your friends who's been curious about these questions too. I hope you enjoyed watching Digital Labs. Goodbye for now. See you next time.